Lesson 13 is called Problem Solving with Functions, and in 13.1 we're going to be looking at graphs and finding key features from them. So example 1 says, during a science experiment, a spring is hung from a hook and weights of various sizes are attached to the end of the spring. As the attached weight increases, the length of the spring also increases. So if you picture like one of those kind of like coily springs, it's attached to something from a hook, and like different like size weights are being added to the spring. And you can imagine like if you put a heavier weight, it's going to like kind of drag the spring downward and increase its overall length. So that's what we're looking at in this graph on the left here. So just see kind of a visual what is happening with the spring. We're putting weights on the bottom of it, so it's kind of like stretching the spring out. So the first question right here, it says, what is the initial value and what does it mean in the terms of this situation? So when you see the phrase like initial value and you have a graph, you're looking at where's the graph beginning, and you're looking at the y-intercept specifically. So remember, like graphs, the horizontal axis, that's the x, and then the vertical one, the one that goes up or down, that's the y. So if we're looking for the y-intercept, we're looking at where does the function touch the y-axis. And for this problem, it starts at 6 on the y-axis, or it hits the y-axis at 6. So our initial value is 6. And what that means, if we look at the y-axis, it says it's representing the length of the spring in inches. So that means that the length of the spring begins at 6 inches, and then it gets longer from there depending on like what size weight is on there. So the initial value is 6. And then we can say for like, what does it mean in terms of context? We could say the length of the spring starts at 6 inches. Okay, so the initial value is 6. Again, one more time, just because that's where it hits the y-axis, or the function itself touches the y-axis. And then that, in terms of this problem, means that the length of the spring is starting at 6 inches and it's getting longer from there. Add a little note before we move on. The initial value on the graph is the y-intercept. Okay, so moving down to the second question, it says, what is the rate of change and what does it indicate about this situation? So when we look at a graph of, well, specifically a linear function, the rate of change, that's the slope, and we interpret it as rise over run. So I'm going to say m, that's like the letter we use to represent rate of change, is rise over run. So we use that formula to find it. In order to find it, I just need to find 2 exact points on the graph. So by exact points, I'm going to zoom in. I mean, like as a counterexample, not a point like this, because you can't exactly tell what it is. It's kind of in between 2 different ones. So for exact points, we would use any 2 where they like cross the grid line. So like say right here and right here, or you could do like right here at the start and right there. Any like ones that are exactly kind of on the like whole numbers rather than like a decimal or something like that. So I'm going to use those 2. So for my rise, between my 2 points, I'm going up 1 unit. But if you look at the side over here, like I'm going from 10 to 12. So I'm actually going up 2. Because you can see like each one kind of square on the y-axis is actually 2 units. And then for my run, I'm going over from, like, it looks like 2 units, but we have to look at the scaling, and I'm only going over from 2 to 3 on the x-axis. So if I'm only going over from 2 to 3, then my run would just be 1, because it's going up 1 from 2 to 3. So when you're looking at like rise over run, you have to make sure that you pay attention to the way that the axis is labeled and not just counting the boxes. So one more time, like, yes, here we went up 1 unit, but we're going from 10 to 12 on the y-axis, so we're going up 2. And then right here, like, yes, we're going over 2 boxes, but we're really only going from 2 to 3, so we're only going to the right 1. So going back to like the rise of a run, rise means like how far up or down are you going? So we went up 2, and then the run means like how far left or right, so we went to the right 1. So the rise of a run would be 2 over 1, or that just simplifies to 2. And 2 over 1 does simplify down to just 2, but sometimes leaving it as a fraction really does kind of help it make more sense in context. So to figure out what it like indicates about this situation, we have to look at the x and the y-axis. So for the rise of 2, that was like how far up or down, and that's like something that we read on the y-axis, and it says the y-axis is the length of the spring in inches. So I'm going to say this is 2 inches. And then the run, that's like the change like side to side. So for side to side, we look at the x-axis, and that says the weight in pounds. So next to 1, I'm going to put pound. And then now if we just bring it back to like what the problem was saying initially, remember we had this little kind of like sketch. So we have a spring and we're attaching weight to it. And as you attach more weight to it, the spring gets longer. So what this rate of change means, like of 2 inches over 1 pound, is that every like new pound that is added to the spring, it's going to get 2 inches longer. So if you go from 5 to 6 pounds, you're adding 1 pound, the spring is going to get 2 inches longer. So you can say the spring gets 2 inches longer. You can just do the double like tick mark for 2 inches. 2 inches longer every 1 pound that's added. And then pound, you can shorten to LB. So 1 pound that is added. So the spring gets 2 inches longer for every 1 pound that's added. And then that's it. That wraps up example 1. So example 2, it says pumpkins are being launched from a balcony using a catapult. Sounds kind of crazy, but it's what's happening. The height of the pumpkin can be modeled by a quadratic function, which is shown in the graph. So it's this graph over here to the right. You can picture like the pumpkin starting here, it's going up, hitting its high point, and then it's coming back down, eventually hitting the ground. So the first question, what is the initial value and what does it mean in terms of the situation? So remember, we learned in the first example that the initial value means the y-intercept. So the y-intercept is where does our function cross the y-axis? And so that looks like this point right here, which is at 20. So our y-intercept or our initial value would be 20. And then now we just want to think about what that means in the context of this problem. So it says that the pumpkins are being launched from a balcony. So that balcony must be 20 feet above the ground because it says on the y-axis that the y-axis represents the height. So depending on the height of the point, that must represent how high the pumpkin is above the ground. So we can say the balcony is 20 feet above the ground. I'm just going to say the balcony is 20 feet up for a little bit shorter, or to shorten it a bit. Okay, so the next one. What is the maximum height of the pumpkin after being launched? So we just found its initial height. And so really like the height of the graph is showing us how high the pumpkin is at any given moment. So if we want to find the maximum height of the pumpkin overall, we have to find the highest point on the graph, which it looks like about right there, which for ours, it looks like it's I don't know, we might have to kind of estimate it because the 45 would be like in the middle, and it looks like we're a little bit above that, but we're not quite all the way up to 50 right there. So maybe let's estimate it at like 47 or 48 feet, and it's okay. It's perfectly okay to estimate, especially if your graph doesn't hit like a specific point. So we can say the maximum height is approximately I'm going to say 48 feet. So the maximum height is approximately 48 feet. And then this one has an extra question. It says, how long before the pumpkin hits the ground? So we're trying to figure out now how much time goes by before the pumpkin hits basically like a height of 0 if it's going back to the ground. So if we're trying to find the time, if you look at the x-axis, it says the x-axis is the time in seconds. So how far left or right the point is going to tell us like how long the pumpkin's been in the air. So if we're trying to figure out how long before the pumpkin hits the ground, we have to look at for when the pumpkin hits the bottom of the graph, because the bottom of the graph has a height of 0, and that would be the ground. So that's that point right there, and it looks like we're going to have to estimate it again. So we'll look at the scaling on the x-axis. So it looks like this is 1, 2, 3, 4, 5, 6, 7, and then 8, and this would be 9. So it's somewhere between 8 and 9. It looks a little bit closer to 9, so we can maybe estimate it as like 8.6 or 8.7 seconds, depending on if you feel like it's a little bit closer to the middle or not. So for how long before the pumpkin hits the ground, we can say about, I'm going to say 8.6 seconds. And again, this is just an estimate. We don't know for sure, but I estimated it at 8.6 because this point right here where it's touching the ground is like in between 8 and 9 and a little bit closer to 9. Moving down to 13.2, this is comparing rates of change. So example 1, suppose 2 companies offer you the same job position. Company A will pay you $35,000 with a $1,500 raise per year. Company B will pay you $30,000 with a 7% raise per year. So we have a couple functions for each company. So company A, they're going to pay you $35,000 with a raise of $1,500 per year. And that function is going to be a of x equals 1,500x plus 35,000. That's a linear function because you're getting the same amount of raise per year. And then company B will pay you 30,000 with a 7% raise per year. And that function is b of x equals 30,000 times 1.07 to the x. That's going to be an exponential function. It's kind of like our exponential growth where it's increasing by 7% each year. Okay, so if you only plan to work for the company for 4 years, which company should you choose? So when you have a graph, all you really have to look at is where is that 4-year mark on the graph? And at that 4-year mark, which company is paying you more? So it looks like on the x-axis, that's going to be our time in years, and 4 years is right here. So anywhere along this line is 4 years. And if I zoom way in on that 4-year line to figure out which company is going to be paying more through that point, you just have to look at which one is higher, because the height of the graph is, if we look at the y-axis, it's the salary. So whichever line is on top is going to be paying you more money because it's going to be higher on the y-axis, it's going to be paying you more salary. So if we're only planning on working for the first 4 years, that's just, oh my gosh, that's huge. That is just this first portion of the graph right here. And that entire section of 0 to 4 years, a of x is higher. It's paying you more than b of x because it has it's kind of landing higher on the y-axis. So if we only want to work for 4 years at either company, then we'd want to pick company A because we would make more money over that time. So if we only plan to work for the company for 4 years, which company should we choose? We should choose company A because we're going to make more money over that 4-year time frame with company A than we would with company B because company B is down here versus company A was up here. And then the second question, it says, if you plan to work for the company for 15 years, which company should you choose? So if we look at the graph and we look at the x-axis where the time is, it doesn't even go all the way up to 15 years. 15 years would be somewhere over here if we kept extending the x-axis. But you can see what's happening towards the end of the graph is company B, because it's exponential, so remember this one was exponential, company A was linear, because you were getting the same amount of raise per year, versus company B where you were getting a 7%, so it's going to increase over time. Company B, you can see it starts to like shoot up, especially towards the end of the graph. It really starts to like, you're definitely making more money than company A, and the more time you work there, the bigger that gap is going to be, because it's growing at an exponential rate, so it's going to be increasing more quickly than the linear one. So for the second one, if you're going to work for 15 years, then you should definitely choose company B, and really the longer you plan to work for either of these companies, the more company B makes sense because it's growing at an exponential rate. The last section, 13.3, is comparing functions in different forms. Sorry, that's a typo. That should be different, not difference. But different forms. So you can see example 1, it says the graph and the table represent two different functions. One function is called f of x, that's the graph, and one function is called g of x, that's the table. It says which function has a greater minimum. So when you're looking at a graph, the minimum represents the lowest point on the graph. So we want to find the lowest point there, which we can see there's a point at the very bottom of the graph down there, and it's labeled -1, 1. So the minimum is referring to the height of the point. So we really just need the y coordinate from that point. So we're just looking for that 1, because that is the height, that's the minimum. So the minimum of like function f of x is 1. And then when we're looking at a table, we want to still look at like the y coordinate of the table or of each point. And remember, when we're looking at a table, the y values are all on the right side. Sometimes it could be labeled as f of x or like g of x or y. But remember that f of x or g of x, whatever the function is named, and y are interchangeable. They both just represent the output of the function. So we're looking at just that right side of the table, and we want to find the lowest value on there, the smallest number. So the smallest number on the right side of the table is 0. So that means that the minimum of the function g of x would be 0. And then now the question is just asking which one has the greater minimum. So one minimum is 1. The other minimum is 0. Which one's larger? Well, 1 is larger than 0, so f of x must have the greater minimum. So f of x has the greater minimum because its minimum, one more time, is 1, versus the minimum of g of x is 0.